Okay, so we come to the Haber process, which is really equilibria applied in a real-life context, a very important context. And that's because the Haber process is all about the production of ammonia, something that absolutely transformed the 20th century. That's because ammonia lies behind fertilizers. Fertilizers have led to a revolution in agriculture, the amount of food that we can produce, the size of the population that we can support generally across the world. So it's an incredibly important process, one with huge economic implications. So its primary use is in the manufacture of fertilizers, in making explosives, and it's also an ingredient in some cleaning fluids as well. So it has the formula NH3. So that tells us it's one nitrogen and bonded to three hydrogens. Both of those are non-metals, so that leads us to conclude that the bonding present in ammonia is covalent. Nitrogen is in group 5, so it has 5 electrons on its outer shell, so it needs 3 more. That tells us that nitrogen is going to have to form 3 covalent bonds. Hydrogen needs 1 more electron to have a complete outer shell, so that will form 1 covalent bond. So our stick diagram is going to look like this. If we then think about the dot and cross diagram, we know that every one of those lines representing a covalent bond is a shared pair of electrons, so we'll represent those as a dot and a cross. And if I look at what I've written so far, I've got 3 crosses. I'm going to say the crosses are the nitrogen electrons. Well, nitrogen is group 5, so it should have 5 crosses in total. So what we have is a pair of electrons that are not taking part in a covalent bond. So they're sometimes, well, they are called a lone pair of electrons, although that is a term that doesn't really feature very much in GCSE. So the next thing for us to consider would be the structure type. If we know that the bonding is covalent, we've really then got 2 choices. We've got a simple molecular structure or simple molecule structure, or we have a giant covalent structure. So it would help us, I think, to have a way of deciding which of those any substance was if we knew it to be a covalent structure. So we would start with a question we've already answered, but is it made of non-metals only? Well, it's made of nitrogen and hydrogen, so yes. We then consider whether that substance consists of more than one non-metal, which it does. It's got nitrogen and hydrogen. Or we could consider whether its formula has any subscript values, which means the little lowercase numbers or the little numbers are below the line. Subscript means below the line. It's NH3 with a little 3 as a subscript. So actually it consists of both more than one non-metal and it has subscript values in its formula. The one sort of caveat to all of this is we just got to recognise that SiO2 is an exception to this. But yes, it's more than one non-metal. It does have subscript values in its formula, so that tells us yes, it is a molecule. So now we've established it's a molecule, we can decide that the structure type is molecular. Now that we know that the structure is a simple molecule, we can have a think about what state it would be in at, say, room temperature. So normally when people are asking about states of matter, they're typically asking at room temperature. So it's a simple molecule. What that tells us is that it has intermolecular forces. Right? So there are forces of attraction between the molecules. So inter means between. And one of the things that we know about intermolecular forces in simple molecules, i.e. small molecules, are that they are weak. And if they are weak, that means it doesn't require a lot of energy to overcome those forces of attraction, which means that, as a rule of thumb, at room temperature, a simple molecule is a gas. And in fact, ammonia's boiling point is about minus 33 degrees Celsius. So let's look at the reaction that is the Haber process. So that's the reaction equation. On the surface, it's a very simple reaction. We have a molecule of nitrogen, 3 molecules of hydrogen. They react together to form 2 molecules of ammonia. You can see that it is an equilibria reaction. So we've got to consider how changes in conditions affect the position of equilibrium. Given that this is an industrial process, we are going to be wanting to maximize the yield of ammonia. We're going to be wanting to produce as much ammonia as we possibly can. Now, the forward reaction is exothermic, which means that the backward reaction must be endothermic. So we can use that information to consider how changing the temperature would affect the position of equilibrium. Both of the reactants, nitrogen and hydrogen, and the product, ammonia, they're all gases. So that allows us to consider how pressure might affect the position of equilibrium. And of course, to decide that, we just need to make sure we understand how many moles of gas are on each side of the equation. So we can think about what conditions we can change to increase the yield of ammonia. So let's consider pressure first. We've got 4 moles on the left, 2 moles on the right. We want to shift it to the right. So we want to shift the position of equilibrium to the side with the fewest moles. The way that we get the system to do that is if we increase the pressure. So if we increase the pressure, the system seeks to oppose that increase. So the only way it can do that is reduce the number of particles that are hitting the walls of the container. So it does that by shifting to the side with the fewest moles. So if we want to increase the yield of ammonia, we need to shift it to the right. We need to shift it to the side with the fewest moles. We need to increase the pressure. So what about temperature? So we want to favour the exothermic direction. We want to favour the reaction going from left to right because we want to produce more of ammonia. So we need to encourage the system to release more energy. So to do that, we have to ensure that there's less energy to begin with, if that's the right way of putting it. So we're going to use a lower temperature. A lower temperature, if we decrease the temperature, we in effect decrease the thermal store. The system seeks to oppose that change. It wants to get that thermal store back up. It can only do that by transfer of energy. That transfer of energy would be from the chemical store to the thermal store. The only way it can do that is to release energy to the thermal store, is to release it to the surroundings, and that's to go in the exothermic direction. So if we want to increase the yield of ammonia, we're going to have to lower the temperature. Now the thing is, in industry, we're not only concerned with yield, we're also concerned with the rate of the reaction, i.e. how quickly do we produce the yield that we are going to get. So we have to think about factors that affect rate of reaction. So the first thing to say is that a catalyst is used in this reaction, and it's iron. So iron is a catalyst, so we put it above the equilibrium sign, so it's a catalyst. It's a transition metal. They do often make good catalysts. So we're going to use a catalyst to increase the rate. Another factor that can affect the rate of reaction is pressure. The higher the pressure, the greater the frequency of collisions, so the greater the rate of reaction. So we would increase the pressure. Another factor that affects rate is temperature, because particles have to have sufficient activation, or have to have the activation energy or greater for a collision to be successful. So we would increase the temperature. So we've considered factors that increase the yield of ammonia, and we've considered factors that increase the rate of reaction, i.e. how quickly we reach equilibrium. So you'll notice that pressure and temperature feature in both yields, or how we affect the yield and how we affect the rate. If we look at pressure, if we increase pressure, we increase the yield. If we increase pressure, we increase the rate of reaction. That's fine, that's fantastic. However, we have a problem when we look at temperature, because if we want to increase the yield of ammonia, we have to lower the temperature. But if we want to increase the rate of reaction, we have to increase the temperature. So they are at loggerheads. They are sort of opposing each other. And so what we're going to consider shortly is a compromise temperature, something in which a temperature where we get a decent yield, but we also get a decent rate of reaction. The only other thing that we've done is to use a catalyst. And the important thing to remember about a catalyst is that a catalyst does not affect the position of equilibrium. It only affects how quickly we reach equilibrium. So this graph shows us, or gives us an idea of how yield is affected depending on the temperature, depending on the pressure. So you can see that the highest line, or the line where we're at maximum, when we get the maximum yield on this, is with the lowest temperature out of all of those graphs, but also at the highest pressure too. So now we can get a better idea of what actually happens in industry. So we've got the actual conditions that are used here. We've got a temperature of 450 degrees Celsius, so that will have been judged to be a compromised temperature when factoring in yield and rate. We can also see there's a high pressure, so 200 atmospheres. That means a pressure 200 times greater than atmospheric pressure. Now, on the previous slide where we saw the graph, we saw higher pressures than that. But pressure is expensive. Pressure can also be quite dangerous. I mean, you've got to have the equipment that can withstand it. So again, this is a sort of a compromise. It's sort of probably considered the greatest pressure that they can do that's both cost effective and safe. And then finally, we have the iron catalyst. So iron is fairly cheap. We know that catalysts aren't used up in the rate of reaction. We know they provide an alternative reaction pathway. We know in doing so they result in a lower activation energy being needed, so we have a faster rate of reaction. So we're going to reach equilibrium much more quickly. So let's consider where the reactants are coming from. So let's look at nitrogen first. And nitrogen comes from the atmosphere, it comes from the air. I mean, the atmosphere is 78% nitrogen. So that's a large proportion, and that's where the nitrogen is sourced from. Hydrogen is produced by reacting methane with steam. So we are using a non-renewable resource there. A couple of other things to say. You can see there's an arrow coming out of where the reaction's taking place. We can see an arrow coming out where it's got the temperature and the pressure and the catalyst. So what happens is that the mixture's cooled, okay, and that means that the ammonia condenses, and then once it's condensed, it can be separated off. Ammonia has a higher boiling point than both nitrogen and hydrogen, which means it'll actually condense before nitrogen and hydrogen. So we can condense just the ammonia and leave the nitrogen and hydrogen in their gaseous form, and that allows us, therefore, to recycle the unreacted nitrogen and hydrogen. So that's why we have the arrow going back into the reaction box. So let's put all of that together by considering the temperature, the pressure, and the catalyst, and how they affect the equilibrium yield, how they affect the rate, and because this is an industrial process, how they affect cost. So a higher temperature means a lower yield. So the forward reaction is exothermic. That means if we increase the temperature, we're going to favour the endothermic direction, which is the backward reaction. So we're going to shift the position of equilibrium to the left. Now let's consider rate. So a higher temperature is going to give us a faster rate of reaction. A higher temperature means the particles are moving more quickly or moving faster. They're going to have more kinetic energy. So the frequency of successful collisions will increase. So more particles will have activation or greater, and they will be colliding more frequently. So the number of successful collisions, the frequency of successful collisions, will increase. Of course, a higher temperature means a higher cost. So it does have that implication too. So if we consider now pressure, so the pressure we're given is a pressure of 200 atmospheres. Well, as we've already seen, a higher pressure gives a higher yield. Remember, there were 4 moles on the left of the equation, 2 on the right, so there are few moles on the right-hand side of the equation. So the position of equilibrium will shift to the right to oppose the increase in pressure. Higher pressure gives a faster rate of reaction. We have more particles per unit volume, so the frequency of collisions increases. There is a cost implication, though, with such a high pressure. Pressure costs money because it requires more energy, but it also requires better equipment, and they have their own cost too. So we've got a greater energy and apparatus cost. Remember, a catalyst has no effect on yield, but it does increase the rate of reaction, and it does this by lowering the activation energy, and lowers the activation energy by providing an alternative reaction pathway. And they're a no-brainer, really, especially as the iron is a sort of fairly common metal, so it's relatively cheap, and yet it has a big effect on the rate. So there is no debate about using that. So that essentially concludes the Haber process. So it's really applied equilibria, but it also includes rate and the rate of reaction material. So it's bringing together quite a lot of stuff that you did in C6, but it's applying it in a specific context. So the next thing to do will be to look at questions that are focused around the Haber process. So if you have any queries, you know where to find me. Thanks very much.